All right, so wrap up our Bessel function. And look, I've seen some of your homeworks already, and I've actually seen a fair number of mistakes. Let me just explain. So if you can correct it, I'll give you till 5, right? I'll finish the next homework and post the next one till 5. Okay, 3D kinetic energy operator with potential, sorry, you should have a hat. With potential, right? Complicated, right? It's still just X, Y, and Z. It's just X, Y, and Z, but you can't use X, Y, and Z for a particle and sphere. You have to go to R theta phi. It's not, that's a round peg in a square hole. It doesn't work well. It looks crazy, regardless. You separate it, the radial captures the energy, so it ends up being, energy's right there. The angular part does manifest, unless you're in S state, in which case this is 0. Angular part manifests here. And then Bessel solved this. Bessel solved this for a ring, and then Bessel solved it for a sphere. And so there's two different types of, actually there's many types of Bessel functions. You got to be insanely careful about it. Sorry, there's nothing I can do about that. There's Bessel functions. Those are a particle in a ring. There are spherical Bessel functions. That's the solution to this. So recall that for an S state, L is 0, that's the definition of an S state. And what we ended up with was, and I know I was really rushing last time, you end up with double derivative of R. Again, no potential. We'll figure out boundary conditions later. Double derivative is equal to k squared times the function. And that's the same problem that we've been dealing with. Did I do this the same? Plus, it doesn't matter which one I think, plus or minus, really. So it's the same problem we've had most of the time. So we have an R now. That only is true for the S state. Yeah, you've got to have at R equals 0, it's got to equal 0. And that's because the wave function itself, remember that this is actually a tool to solve the actual wave function. So just recall that. So the real wave function is this thing over R, and that means that R equals 0. To avoid infinity, the boundary condition is R of R better be 0. Okay, and so, therefore, A is equal to minus B, right? You have 1 minus 1 is 0. And the wave function is then sine KR over R. And then there's a normalization constant, which you can figure that out. Okay, what am I? Yeah, actually, I'll write down the normalization constant here. So there's a normalization constant, and you're done. There's P states, right? So Bessel solved Bessel functions. Those are for rings. Spherical Bessel functions. Those are for this. For P states, had to solve a different problem with that thing there. Okay, when it comes to the normalization function, you're going to integrate R from 0 to A. A is traditionally in a lot of material science, and I'm kind of doing a material science problem here. These are like quantum dots. Particle and sphere. The electron, if you hook up a semiconductor quantum dot to some wires and introduce some juice, that's the electron. Electron's in a spherical trap. If you shine light on it, the electron's promoted from the ground state, there's your electron. It's in a trap, it's in a spherical trap. So the letter A is very frequently used as a materials parameter. So A is the radius of our sphere. If you look at unit cells of solid state materials, the size of the unit cell, letter A. So you see the letter A all the time in material science. Okay, if I'm going from 0 to pi, I can tell that's the theta integral. And if I'm going from 0 to 2 pi, that would be phi. Phi does this, right? And the theta does that. So it's really terribly important you keep that straight. Now the whole thing is the Bessel function, by the way. It's not just this part. It's R over R. That's the whole. This whole thing is, again, traditionally J order, where order is SPD, spherical Bessel. Okay, now don't forget this, spherical harmonics. And don't forget, sorry. Okay, now, oh, no, wait, no. I have to do, I think these two, is this right? Does it go? It goes like this, right? Yeah? You think so? Anyone else? I think so, yeah. I did this on the homework, so I hope it's correct. So again, I mean, look, if you get the units, the limits, and you get this variable wrong, you're really going to screw up. Right? So here's something I do on the homework, so you don't get just screwed over here. I actually would. So if you're being careful, you can do this. Make sure you know the things are. Okay, and of course we have some kind of, you're going to figure out what n is, n squared is, so that equals 1, right? So you have to normalize it. I have it written down here. You just figure it out. Mathematica. Just use Mathematica. Okay, I can tell you that Mathematica will actually say that this integral, which should be just like, it should be like 1/2 n squared, right? If then n is the square root of 2. 1 over the square root of 2. So something, yeah, something like that. Actually, I know for a fact Mathematica can do 0. That's bad. Your normalization should be a number times n squared. And n squared then is 1 over that number square root. Sorry, n squared is 1 over that number, n is 1 over that number square root. If the return is 0, something's gone really wrong. What went wrong? What did you do wrong? Notice I left, why did I leave the space? Why did I leave the space? What did I do wrong?
You have to multiply everything by R.
Multiply, you're half there. Almost. You're guessing. You know what that is, don't you? Why am I multiplied by r squared sine theta? Tell you what, what's this? 0 to r, 0 to pi. When you integrate, nothing, you're integrating volume, right? If I integrate dx, dy, dz from 0 to L, the answer is L cubed, the volume of the cube. So this should be the volume of the sphere, right? Do you agree? It's the volume of the sphere. 2 pi squared r, that's the result. It's pretty far off. All right, so guess what? What happens if I do this? If I put in r squared sine theta, you know what I'm going to get? You know it, don't you? You knew it. Yeah, I don't think you should just walk through it. Hopefully when you're 90 years old, you'll still remember this. Jacobians. All right, don't you remember Jacobians? Wait, you folks, you're kind of looking away. That's scary. Do you know what a Jacobian is? Okay, all right, that's terrifying. You should know what a Jacobian is, right? When you transform integration in x, y, and z, which is natural, and just spits out volume without you doing anything. Just like I just said, dx, dy, dz from 0 to L is L cubed. That's volume. It makes perfect sense. You don't have to think about it. But when you transform to r theta and v, again, r theta and v is just not, it's just a round peg in a square hole. And it requires a translation so that when you're just integrating the variables, it returns volume. R squared sine theta is the translation. So if you forget that when you're doing this, it's not going to normalize right. You're going to get junk. So anyway, I just wanted to point that out. And last bit, all right, so one thing I noticed was on your homework, if you want to send a correction, the spherical vessels are not the same as the vessels. So the way this looks, this would be n equals 1 state for n equals 1 S state, and then you would have a, sorry, what do you mean? You can have n equals 2 states, which would cross, which would have one node, so that's an n equals 2, still an S state, and then you could have an n equals 3. Screw this up. So this is the actual wave function. So this is the actual vessel function. So it's R over R. It's this is this. So you see that you can have multiple S states. You can see by the amplitude of the R axis of the y-axis. The number of nodes has to do with the n quantum number. And then you have p states. And of course, all of this ends at A, the radius. Okay, p states look like this. They're very similar to hydrogen. You would have a n equals 1 p state. Then you would have a D state. This would be a P state, that's a D state. And actually, it has to squelch over if this is A, so I didn't draw this quite right. Anyway, so you can graph these, whatnot. The thing I wanted to point out was I noticed on the homeworks I got already that you were using vessel functions, zeros, to do your calculation. You're not supposed to use vessel function zeros. You're supposed to use spherical vessel function zeros. They're not the same zeros. Okay, so anyway, if you mess that up, just send me a correction because it's wrong. So anyway, I just wanted you to be careful of that. So what I wanted to do today was do atoms. So I want to look at hydrogen because we're kind of here. Hydrogen, and then on your homework, you're going to analyze the helium atom. The hydrogen is done at an undergrad level, and I don't have my silly textbook written for a hydrogen atom, but it's not hard to look up. All you've got, I mean, there really is actually very little to say at this point, despite that relative complexity of how all of this works. All you do differently is you include the potential, which is negative, which is downhill, which is the electron interacting with the nucleus. Now this is now the trap. So instead of the electron hitting a wall of infinite potential energy that keeps it in place, instead the Coulomb potential keeps it in place. So the radial Schrodinger equation looks like this. And I'm going to put this slightly differently because this is the same thing I did before. But I generally see it written this way. So instead of the wave function being some radial over R, instead you can just do the opposite. You're solving for this thing, which is the real wave function times r. I believe it's exactly the same thing I did before. It's just that this is how you're more likely to see it if you look this up on the web. Okay, so there's the angular part, of course, multiplied by a function. The electron interaction with the nucleus. And the reason that you want to represent it this way is because those r's cancel out, and that just makes it easier. So when Schrodinger was solving this, notice that Schrodinger just looked for a generic function here, and then divided by r to get the real wave function. So it's the same thing that we were doing before. I'm just showing you this way because this is how I find it in textbooks. This is how I find it on Google. So I don't want you to look at this and get confused. Where it does something kind of funky is that the potential energy is negative. Right, so here's a 1 over r upside down. The 1s state is like at minus 13.6, I think, eV. And then you get the 2s. The 2p is the same. These energy levels get really, really, really close. Energy is proportional to 1 over the principal quantum number squared. So it's just kind of funky that the energies are negative. I don't know of any other quantum problems that have negative energies. It doesn't matter. Energy is relative, right? If you're going to do spectroscopy, you're looking at changes between energy levels, and that's positive. So it doesn't matter if the absolute energies are negative. Or I can just take the whole thing up, and I can just add 13.6 eV to the numbers, and nothing changes. Right? Draw it up there. Draw it however I want. Energy is relative. So that's kind of nice. Okay. Now, of course, you look up. Actually, Schrodinger, I think that the solution to this was not in an 18th century math textbook. I think the dude had to get a mathematician to help him with this. I don't think the answer actually existed. I think it's called like Laguerre polynomials or something. Anyway, I don't really care. Let's do an S state. And so on your homework, you're going to be looking at the S state of a helium atom. And of course, traditionally, we call the wave function with the angles, we call them y instead of that Greek y and psi. Okay, so if we're doing, another thing you can do, here, let me put this like this. I'm going to call this H Mike. Okay, this is when you solve the Schrodinger equation for hydrogen-like. Now that means hydrogen is like hydrogen. Oh god, wait, what was it? Helium plus. Helium plus is got 1 electron. Lithium 2 plus. Lithium 2 plus is 1 electron. So 1 electron atoms. What you do is you just use a different atomic number, and that would go here. That's what it goes in. And it affects the number, it affects the results. Let me show you how. It's relatively simple. It changes the normalization. A naught is a bunch of constants. They're in units of meters. It's called a Bohr. I'm sure you've heard of that. It's about half an angstrom, 0.52 angstroms, I believe. Okay, so it changes. So if Z is bigger for like lithium, helium has 2 protons, lithium has 3. Notice that it will draw the electron closer, and so that's why you get e to the minus ZR. Draws it closer. So that makes sense. And then it affects the normalization. For an S state, it couldn't be easier. The spherical harmonics are just constants. There you go. All right. So there you go. And then just, you can look up P states. You can do that on your own. whatever. It just, here's the Diffie-Q. Some geezer back in 1930 solved it, and they made tables like this, and then there you go. You can do lots of analysis. You can do lots of analysis with this, and world fantastic. Okay, now on your homework. So now again, I do this for undergrad. So what the hell are we doing here? All right. If you see your homework, you're gonna be so bad. It's crazy. It's easy, but it doesn't look easy. But that's kind of what you want in grad school. Okay, let's do helium. He, not plus, because I've already done it. Let's do He. All right, now I would contend that I'm missing something. All right, now this can't be done for He as an extra electron. Something's got to be different. You can't just add electron and have nothing change. That doesn't even make any sense. Well, you want to start at the Hamiltonian, because that's how you start everything. So what do I need here?
Something to account for the electron fault.
Exactly. All right, let's add a term. Okay, now it would be positive, minus E, minus E squared, 4 pi E naught. Absolute value, that sucks. R sine of R. Okay. Now, now again, even Schrodinger, when he just had hydrogen, I think he looked at this and said, "Oh, I don't know. I've seen that. This Diffie-Q. I haven't seen this Diffie-Q in a math textbook. Maybe he did. I'll try to look it up. I'm kind of curious now." As usual, you go find an 18th century math textbook to find the solution to this. Heads up. You can look forever, you'll never find it. Right? The reason is, now remember, whenever we approach these more difficult this is multi-dimensional. Any multi-dimensional deal is approached this way. Okay, and I'll use very specific, I'll use language appropriate for problems. Normally I'd say psi r, psi theta, psi phi, but I'll be more careful. We call them spherical. I don't know that they would be spherical harmonics, but I'm going to try to find them. Okay, so normally you do that, and then you separate terms, and then you solve, then you get many Schrodinger equations, and you solve them. Now here, you have to have the separated, and it's more complicated because you're going to have to get terms with. So you have twice as many dimensions now. So you see, you actually have 6. You can have 6 separable Schrodinger equations. That sucks. Think about this. How do you separate that? How are you going to get an R1? You can't have an R1, so you got an R1 and an R2. Now, these have to have a plus or a minus. They have to have a plus or a minus between them. Now, I'm not seeing, 1 over minus doesn't work. That's in the same term. That's in one bracket. But actually it's in 2 brackets simultaneously. You can't do that. So what do? How do you break that up? Huh? The answer is no one knows. It's impossible. It's a mathematical impossibility. There's no solution. See this? Did you notice that your undergrad you stopped at hydrogen? You had to. There's nothing more. You can't solve it because it's inseparable. Now also think about what this does. You can't have this go to infinity. So whatever your solutions look like, I didn't really do this right. See, I didn't even quite do this right. I should have done. I'm not going to write them all out. Anyway, you get my point. The reason that this is impossible is that the wave function for R1 has to somehow avoid R2, that they can't overlap, right? This would not allow overlap, this would be infinite energy. R1 has to be able to respond to R2, but the function can't contain R2, right? Because then it's not separable. So how do you get R1 to never be where R2 is at, but never tell it what R2 is, right? Well, that's a mathematical impossibility. And it is. That's ridiculous. You can never do that. Real mathematicians looked at this and said there is no solution. That's right. There's no solution like e to the r sine theta. There is a solution on a computer, hence mathematical. Okay, so heads up on that. And again, now you see why we don't talk about this stuff as undergrads. Okay, next thing. Okay, you're going to love this. Okay, you know what you're going to do? So I'm pretty sure you're aware that we're doing quantum mechanics on atoms other than hydrogens, in hydrogen light. So how do we do that? Programs like Gaussian, have folks heard of Gaussian, QChem, programs that do quantum mechanics on big molecules. Okay, so for the He atom, we're going to do this. Ground state, right, the ground state. We are going to use this wave function regardless. And in your homework, you're going to keep the z there, and you'll see why. I know z is 2, but leave it. And I will explain why in a minute. Okay, so there is, here's the radial, and I'm just going to combine the angular too, because it's kind of stupid not to. Okay, that's electron 1. Here's electron 2. And notice I'm just writing the same thing twice. Oh, I need to put subscript, sorry. R1, R2. And R1. Again, z is 2, but don't worry about that. Okay, so that's the radial. So no, that's the total wave function. That's the total wave function. All right. Now notice what I've done is I've used a hydrogenic, I've used the He plus wave function. It's correct for He plus, but this is not He plus. I've used the He plus wave function, I've written it down twice, and of course that's because the configuration right is this. So ground state, right? I mean, you're teaching freshman chemistry, right? So you know that. So I've just written it down twice. Okay, so I'm just going to use it anyway. Is that a problem? Okay, what happens if I do this? What happens if I do that? Now, you know I'm trying to get the energy of the helium atom. How's that going to work out? What's the purpose of applying a wave function on the right of the Hamiltonian? What do you get? Right? I mean, that's my purpose. How's this going to work out? They're both, you know. So traditionally you would say psi 1 R1, psi 2 R2, but they're both in that state. So anyway, just be careful of notation. Is that going to work out very well? What do you think? You see what's going to happen? You see what this does? This thing has to get wiped out by some other term. Specifically, it needs to be wiped out here by the kinetic energy. But it didn't, because these ain't the answers. If these aren't the eigenfunctions of the Hamiltonian, you do not get the eigenvalue equation to work. That's the whole point. This ain't going to happen because the wave functions aren't going to come back. The wave functions are actually going to be trapped with this term. So you're going to have these here on the left, and on the right, you're going to have that times that, because you ain't getting rid of it, because it's not separable. So the eigenvalue equation fails. So that sucks. And there's nothing you can do about it because we have no idea what the real wave functions are. Okay, but I can still do it. How can I do it? What happened when you had to get momentum of the sine function? Because the derivative of sine is cosine, but we still were able to derive the momentum. How do we do it? Now remember, momentum is d dx, h bar over I d dx. When applied to a sine function, the derivative of sine is cosine. The eigenvalue equation fails. Right? We did that the first week, yet I know that the momentum of the sine function is 0. How did I know that? How did I do it? This was 2 weeks ago. Huh? How did I figure out the momentum of the sine function? Right? This does not equal, does not do that. So what did I do? Huh? Did what? Expectation value. Right, you do remember this, don't you? Right, psi star moment operator psi. So what you do is, now fortunately you notice that all the functions are real. You see what I'm setting you up to do on your homework? See how you're going to do that? 2, 3, 4, 5, 6. Yeah, how much fun is that? Yeah, guess what you're doing? Yeah, you're doing this on your homework. You're going to love that. No, trust me, it's fun. Here, let me get the delete. So seriously, this is what you're doing on your homework. Now you can see Mathematica is going to make this. I told you, I am purposely scaring you because, I mean, look at that. Now, how many terms does H have? Oh, 1, 2, 3, 4. 4 terms. 4 terms, this wave function, 6 integrals. You'll get through it. I mean, you know, I'm not about to say, oh, but it's actually easy. Oh, no, you're actually going to sit down and do this. And it's going to take a while, but Mathematica will make it easy. So remember, if you can do this, you're worth a fortune, right? Look at that. If you can do this, you clearly are worth a fortune, and I'm not giving you much choice. Now, last bit is I'm going to make this even worse. Now, this time I will make it worse, and then I will make it better. Actually, before I go into some detail, but then I undo the detail, let me point out what you're doing here is that you're going to get the energy as a function of z. Okay, that's fine. Now you plug in z of 2, and that gives you the energy. Now here's the thing. The energy is wrong because the wave functions are wrong. So what the hell are we doing? Well, number one, in terms of using this, I don't have a choice. It's either this or nothing. Seriously, it's this or nothing. So, hey, have at it. And we have to live with the consequences of the fact that nothing we ever do is really ever correct. And that's not a joke. Okay, but you can, there is a trick. There's one trick to making it better. Okay, and this is called the variational thing. It's called the variational theorem. Okay, so our wave function, what am I doing? Our wave function is wrong. But there is a, so our wave function, this thing, is wrong. But it is equal to the real wave function plus okay, so now you may recall from my silly textbook that I've said this a couple of times. the complete set of eigenfunctions of an operator span space. Now, what that means is take momentum. Take momentum. Now, remember my textbook where I drew all the momentum states, right? And I said that you can sum these to equal a Gaussian. So if you have a bunch of waves of one operator, you can sum them to equal anything. So if my cat drew something, if I have enough waves, and there's an infinite number of waves, right? You see how there's an infinite number of waves? I can sum this basis, this infinite basis of the momentum eigenstates. I can sum them to equal anything. So that's what it means to span all space. There's nothing here I can't draw that can't be represented this way. Okay, now my wave function in R state at V is wrong. But it can be represented by the real helium wave function, which I don't know, that sucks, but whatever, plus the excited states of that helium wave function, because they span all space. Now, I wrote it this way because there's only one ground state, and then there's excited states. So now looking at this, you tell me, is the energy of this greater than or less than the ground state energy? The energy of a ground state plus excited states is greater or less than just the ground state energy? Great? Greater. Yes, it's greater. It's greater, right? Now, this is called the variation theorem. What it means is that when you do this, and you are going to do it, when you do this, the energy is too high. So what you're going to do is take the derivative and set it equal to 0 and calculate an optimal z. You're going to change the z from 2, you're going to lower it a little bit. And you're going to get a better energy. So what that's doing is, this is a boo-boo and that's the fix. It's not quite right, but this is the best you can do. Now, what theoreticians do, so one reason to do this is, for one, it's a great math exercise. Number 2, it gets you more immersed in atomic quantum theory. Number 3, this is what theoreticians do. They get hydrogenic wave functions and change them. But for hydrogen, it's fine. For other atoms, it's not fine. So what they do is they start with hydrogenic wave functions and they change them, often adding functions or whatever, and do this. They try to find the lowest energy for molecules, and when they get a good result, they publish it. So this is what theoreticians do. It's kind of dry, but it's kind of important work. So anyway, so you're doing the same thing. Now this was done in the 80s, but instead of being stuck in the 20, we're mostly stuck in 1920 in this class. We're now caught up to 1980. So I hope you like that. Anyway, now I can also tell you that the real problem is going to be the Coulomb operator. Now, what you have here is when you integrate, let me just wipe this out. When you integrate a function of R1 and a function of R2, you still run into the separability problem, right? Because what you have to do, you have to turn it into this. You have to do this. The solution, by the way, is absolute value. You represent this as a series. Change the representation, right? You can write Taylor series out of anything. So what you do is, you don't use a Taylor series specifically, you use a Legendre, the addition theorem of Legendre transforms, whatever. It's a formula, I give it, and you're going to work it. It looks bad, but anyway, that's part of it. Okay, last bit. I wanted to also point out what spin does. Now notice that I said before that this is the configuration you're working with. Okay, we're spin. We're spin here. Where do you see spin? You don't. Who knows what spin is? Other than it's an arrow pointed up and down. Huh? To be blunt, it's an arrow pointed up or down. We don't know what spin is. Spin behaves like angular momentum. It behaves like an L of 1/2. So electrons, other than having like SPD angular momentum, they have an additional angular momentum. It's a gyroscope spinning on top of a gyroscope. The big gyroscope is like a P or a D whizzing around a nucleus. The little gyroscope is the spin. And it's less, it's spin 1/2. Now, the problem is we don't think it's actually spinning. We don't know what it's doing. But it behaves like it's spinning. We're going to spend most of our time in this class talking about that. But we don't actually know what it is. Now, as a result, what you do is, to model it, we create spin wave functions. Spin wave functions for a singlet are just called alpha and beta, up, down. So up, down, right? Just like I drew it, up, down. Now, if there's a problem, what if I did this? What if I did this? Is that okay? No, that's not allowed, right? You can never do that. Okay, now because of that, you have to write spin wave functions as an anti-symmetric pair. Now the reason is that notice that if I tried to put them both spin up, see what happens? Zero. Yeah, 0. Okay, so this is, you probably have heard this before. You have to anti-symmetrize. You have to anti-symmetrize your wave functions. And that's what that means. What it does is it models this behavior correctly, or lack of that behavior. It models that correctly. Now, another thing is, so I also have to divide this by the square root of 2. Now, the actual wave function, by the way, I need to do this to you. You also have to make sure that you can't distinguish between electrons. In other words, it's foolish to say that you know the difference between electron 1 and electron 2. So that means that you have to write the wave functions this way for a singlet spin. A triplet state looks like this. Now, I just said there's no triplets. Yes, there are. You would just have to have psi 1 and psi 2. You would just have to have different psi 1 and psi 2s. You'd have to have 1s and 2s. Okay, so for triplet states, which again would be up, up, down, down. All right, so you can't play with that. You can't have anti-symmetry here. So instead, you put it in the space bar. So I just want to point that out. Okay, now in your homework, you're going to notice that you don't see this. The reason is because psi 1 and psi 2 are the same. And so what you end up with is 1 over the square root of 2, 1 over the square root of 2. These are the same orbitals, so it ends up being 2. Okay, so it ends up being this, 1/2 of 2. Ends up being this, but what I've done is I've set up the Hamiltonian evaluation such that you actually don't have to worry about this. I've actually done all the this, that, I already worked them all out. So that I only leave you integrals that are correct. So you don't have to worry about it. But I just want to make sure that you know that it's actually good. Anyway, yeah, what I'm doing